we're going to start with nuclear chemistry. Okay, so first we got to make sure this guys have a clear understanding. And let's say we have this thing. Okay, so this is called potential. Hold on. Here. The nuclear sequence, correct? Okay, so now, how many protons? Protons. 84. Okay. How many neutrons? 4. Anybody want to give another answer? Neutrons. You're supposed to subtract that number. 214 minus 84. 130. Is that 130? Okay. And then how many electrons? Finish first. Electrons, yeah. How many? They don't. Okay, why is it 82? Right? All in charge that it I mean, yeah. More protons. Yeah. 2 more electrons. So that's a positive charge leads to 2 electrons. So that means it's up to 0. Now it's 2, right? Okay. Questions? Concerns? Yeah. Now, let's talk about the nuclear cell, right? Now, this is going to be very vital to pay attention to the nuclear cell chemistry. Yes. Yes. It's up Monday. Feels like a Monday. It's a Tuesday. It's our Monday. Okay? I have no idea. It's been a long week already. What's that? Oh yeah, it was. I see you want to change clothes. So now nuclear chemistry is not as hard as we want to make it out to be. So pay attention to the nuclear cells, right? Because they at the end of the day, we're gonna have to add up. It goes back to that long conjugation. At the end of the day, they're gonna have to add up. Okay? So first off, nuclear chemistry. What is nuclear chemistry? Is just a study of reactions of atomic nucleus. Right? What's in the nucleus? And neutrons, right? So we know that protons and neutrons are the nucleus, and we know that electrons happen inside. So when we're talking about nuclear chemistry, we're looking primarily at what? The nucleus, chemistry, right? Okay, so it was discovered by Henry this yearly, actually, but he actually discovered recently radioactivity. He recognized that radioactivity. Now, radioactivity is just a spontaneous emission of rays or particles of the atom. Okay, so there are 3 different types of radioactivity. Three. Yeah. Alpha particles. Yeah. Beta particles. Yeah. Yeah. Alpha particles. They're going to be positive. Now the alpha particle is going to be made up of just the helium nucleus. Okay? So if it's just the helium nucleus, if it's just the helium nucleus, and we're just looking at the nucleus itself, how many protons are in this? There's two. How many neutrons are in the nucleus? Two. So what's the weight of helium? The weight. Or its mass. 4. Okay. So when we talk about alpha particles, again, it is just the nucleus, right? So if it's just the nucleus, what's the charge of just the nucleus? Positive or negative? Positive. Alpha particles are positive because all it is just the nucleus. So if we have a negative component, an alpha particle is going to lose what's the negative. Okay. So alpha particles are written like this. That's the simple for alpha. So we just use the symbol just look at that. That's not that. Sure. That's a look at it. Crazy. It would move towards a negative charge. It's positive, right? That's opposite. Okay. Now beta particles are going to be high energy electrons emitted into the nucleus. Right? So they're going to be these high energy electrons are strong. So their symbol, first off, the charge of the so their symbol is going to be E, 0 up top, and negative. Okay. Because it's kind of like a movie, a proton. Okay. So gamma rays, they're just going to be electromagnetic conditions. They're not going to have a charge system. They're not going to be positive or negative. Okay. And they're just going to be rays, right? Okay. They're going to be high energy. Okay. So this one's positive. This one's negative. This one's negative. Okay. Now, typically when we see gamma, they use the star. Let us know that it's gamma rays. Now, we talk about alpha decay. Alpha decay means that you're losing an alpha particle. So we have a transformation of a atom that is losing an alpha. Now, if it's beta decay, that means that we're losing that high energy electron. Okay. So decay means that you're losing. Does that make sense? I'll show you specific. Yeah, beta decay is that you're losing that high energy electron. And then alpha decay is an alpha particle. Okay. So here, this represents our radioactive material. Now, this radioactive material is alpha, which we go back to the material, the alpha particle is going to move towards that opposite. Why is it going to move towards move towards the negative? Why is it going to move towards the negative? All because so it's going to be moving towards that opposite charge, right? Okay. Now beta particles, it's going to be moving towards the positive. Why is that? Yeah. And gamma is going to be able to shoot straight through without having to. And so that's going to be kind of important because that's how we kind of control radius. Right? So control alpha particles. That's actually what's actually. Awesome. What's that? So if we're trying to get it to move towards the direction, we don't want it to shoot out. How would you control it? If it were out. On that? A negative. Okay. So you're thinking of the fact that it's electrostatic forces sit there and control that really like to. It's alpha particle, the weather. Makes sense? Gamma is out of control, right? And control. So that's one reason why gamma is so bad. Gamma is. Okay, so we look at alpha particles. Alpha particles can be reflected by that's very. Okay. Beta particles, well, you need lead to sit there. Beta particles. And then gamma particles, well, you need a really big old thick lead to sit there. Yeah. Okay. So now you guys know what you know. You guys are brilliant, right? Yeah, say brilliant. Okay, now let's think about this. Now you guys go to some dentists. You know, some dentists are great. A little chill. What do you think is that? Yeah. Well, oh, man. Okay. Lead. Okay, so lead. Good. So, why do you think they put lead on? What do you think they're using? Radiation. So they're using radiation to sit there and see your teeth, right? They're well. And so when we talk about X-ray, we're basically being exposed to forms of radiation. And guess what that radiation is? Lead. Yeah. Beta, right? Because guess what? Gamma, I mean, it has to be, think about it. Say it's heavy, you have to have lead like this, technically. Is it that heavy? I mean, those jackets are not this thick. You know, they're like this thick. You know, they're barely that thick. So you know that they're right. Okay. So you know that they fall into the beta radius. So we're going to X-ray stuff. So the way that we detect radiation, there are a couple of ways. One of the most common ways of detecting radiation is film. That's why we're able to use that X-ray. Sit there, look, right? Walk it, and then it picks up everything that shoots through, and then it goes out. So there's also called the cloud chamber. So the cloud chamber basically uses the fact that so we know that alpha particles are charged. Positive beta is charged. So what happens is that these supersaturated beta, is extremely sensitive charges. So it will move towards a charge or move away from that charge, depending on whether it's positive. Okay. In the case of they're trying to find out the weak part or no. So in this case, they're trying to see whether or not the radiation. So there's a closed container system. It's like put the rock in this. it makes it's super saturated. Because it's super saturated, right there on that curve, it's also going to have charges associated. Because it has some charges associated with it, it's going to work. It's beta reduces. Yeah. So, in the case of instruments, it's called a Geiger counter, and it's really called a Geiger-Muller counter. And so what it does, it actually and so it picks up that radiation charge based upon that those positive plates. And then it'll send that signal, and it signifies noise. So it'll be yeah. Geiger. What was that? It's like a practice, right? Good. So practice. Okay, so another instrument is called simulation. Simulation counter is basically liquid that you put with the radiation or something to do with it, and it'll actually really start out and also data whether or not you have it's present. And then the last one is called gamma counters. What do you think of the gamma and scanner is testing? Yeah. Yeah. Okay. So here, this is an example of film. So this is how it works. You have a radioactive source, you have a film on the outside, and the radiation breaks and expose parts of the film. So to make that part of the film. And so we expose it, right, except for that part. Or in the case of your teeth, right? So we expose everything outside of your teeth, except the teeth. Right. Or bone. Yeah, questions again. Okay, so in the case of the Geiger-Muller counter, it's going to detect the measure intensity of your radioactive emissions. So what you guys got. So it's going to make noises. Those are going to be counts for the radioactive. So the hotter something is, hot the hotter it is, the more it counts. The lower it is, it counts. The less we get. Okay. In the case of the simulation counter, it's gonna it uses basically transparent solid that uses photoluminescence to observe. So again, you put the stuff in solution and it's a radioactive sample. And it's gonna basically use solid that's in red. So that was typically the process. Geiger counter is a ballpark figure, so we can count a lot more specific. So we talked about photofluorescence, right? So basically that's just the emission of light by a substance after it photosynthesis. Use something to excite, like right? So it's kind of like have you guys ever seen the little toys that you put up to the light and then it starts to go? Or the t-shirts. Those little t-shirts where you stick up light and then you turn on the light and close. So it's kind of like yeah. So in other words, what happens is that was that's it for energy, right? So in that case it's for radiation from the sun, right? And so sun makes it so it's a certain amount of radiation. So during that sun radiation to sit there and excite that the fluorescence, the fluorescence. Pretty cool. It is. Yeah. What was that? Yeah. Yeah. So here's how the Geiger counter works. You basically get sample radiation. So that radiation basically will cause it's using iodine, so it's going to be alpha or a big part. So if it's alpha, this here is cathode. Cathode means that it accepts that whatever cation, it's a positive rate. Don't look at the board because that's cation. Let's see, don't forget.
No,
Okay, so we know a cation is positive. Cathode means that it accepts positive charges. So that means it's going to have a negative. Right. Okay. We said like never. What were you smoking during those days? Did you say something? Okay, so. Yeah, triplet so fast. What was that? It was like a race. I heard that they go out. Yeah, they didn't want to go back, so they went. Anyway, so depending on whether it's a alpha particle or beta particle, it's going to either go to the cathode or to the cathode. And then that's going to send a signal that's amplified. So your voice. So at the end of it, you get that. Right? So that's an example. That's just a modified, right? You see how these big old machines about this. That's two technologies. This is a simulation camera. Now it's literally out this big. Right? It is no joke. Right now, they probably have one thing about this. Technology has changed. Look at right? And when I was in grad school, I used to work with radioactivity all the time. That room, the lab was so high that we'd have to sweat. This here, this is our gamma scanner, right? The gamma scanner. So basically, in other words, if they're taking a look at what they'll do is that they'll do it. They're actually some stuff that's gamma rays, low radiation gamma rays, some of the stuff that work. Guys actually have run this. Not something to kill you, but it does something. Gamma rays again are so they're looking for bigger size.
Gamma rays are really cool. Like when they go into
I don't know if they're full.
not like cold, like I heard something like Vanguard and stuff.
Yeah.
Like
So that's so well. Yeah. So in that case, they probably injected with something that's a lot of contrast. Then that's necessarily makes the house yeah, it's cool. So radioisotopes, isotopes. So we often call them radioisotopes. So you guys are familiar with isotopes, but radioisotopes. So a lot of isotopes are radioisotopes. Now, for us, there's a lot of harmful effects that happen. One of them is that it will break chemical bonds. So the breaking bonds, which break fission, and the radiation properties, fission, and you guys are or cancer. So radiation therapy is one of the most common use. It basically will kill tissue, but it also kills it's often very targeted music, but it's still REM, and that's looking. We basically use this as those absorb. So if you exceed more than 600 REMs, it's a so you don't know that. So like for instance, it's not just radiation. You want to make sure that those and often as well, if you're a person that's working with radiation, like looking at water radiation, be separating status. That's that's so big. So before it's done. Okay, so sources of radiation. We're going to get rocks, water, atoms. So in other words, pretty much nature. Right? So this here basically gives you a breakdown of radiation. 80% of all radiation. Only 18% of it. Another 18% that's made without the need for medical X-rays. Medicine for process. We use it for and then we have all of this. Now you see here, fuel cycles. Right? Very low. Okay. Now, if we look at the natural sources, we have most of it is radar. We have 80% of it as cosmic. 80% of it is basically on Earth. And then we have 11% of that, which is inside surface fire. That's how we do boxes, or we that's how we separate stuff. Almost all submarines are. So there we got. Well, that's good. If you did that already, okay. So when we talk about reviews, we often talk about its half-life is where okay. So half-life means that that's the point where that half of its energy, half. We'll call it weight in most cases, because we're saying this much of it is half, this much of that weight is half radiation. So a lot of times when we think about half, okay, we think about stuff being broken down. In this case, we're talking about part of the active terminal. Right? And that alpha particle, and the way that we determine we calculate half is that this equation. Okay, so it's going to be S represents sprite quantity. R is going to represent the main amount. And then N represents the number of half-lives that they went. And so, you remember this equation with the okay? It's really easy because we have 1 half. That means that's how many half. Yes. So half-life is when you get half of the sample. So radioactive material that's radioactive half. Then it gets to the point where it's only half of reactive. That's considered. Okay. So it starts off, okay, I have this count, and then all of a sudden it comes down and say, yeah, 4 counts. Then it gets down to 2 counts. That could be exact. So you're at half the amount. So we often will associate this quick from that. 28%. Yes, David, you see it here. Okay, so half-life the cake, I'll show you this. So in this case, we're going to basically use this to basically determine that. And so this here represents the half-life of the cake. See that it's an extra one, an extra third. Half. Okay, so if we take a look at this here represents the decimal of the main material. Well, let's start off with one that we have 100%. That would be one. So the half-life would be that 50%. That would be the first one. Okay. So if we take 50% one, and then we continue looking at half-life of half, what is half of one half? 5, right? So then that would be second. So this here represents the first half. This here would represent your second. This here, what's half of what? Half of what word is this? 8, right? So this would be the third of that. And then 1/16 would be the fourth half. And then 1/32 would be the half. Or so that's 1 half-life, half-life, that's 3 half-life, 4 half-life, after. Okay, let's see that. Okay, so if we were to do this equation, what is the equation again? R. Okay, where n in this case represents n would be our right? And we assume that our starting point is this. And so what I would do is so start with 1 gram soda. Back to soda. Then you go 1 to the power. And then that would be this question. You guys are calculating. Good. Get what I was supposed to. Just let's say. Yeah. This is an example of calculating. Yeah, 1 gram of material. We're calculating R. So this is 1 gram. Oh, that's our starting. So that 1 gram of material. And then how we can. Point 0 so that's how much we have to follow. Okay. Question? Concerns? Cash? Kool-Aid? Profits? Okay. Well, words. Life cycle learner. They just happen. Well, R is going to be with me. Let's say that. After what's so long. Say bye. Okay, so here's our problem. The half-life of bismuth 210 is 5 days. If we begin with 60 grams of bismuth how many grams do we have left? 5 days. So in this case, our R's, our S is going to be what? 16 grams. And the number of half-lives that we go through? So 25 divided. That's going to give us 5 half-lives. That's if we get one half-life, we put that 25 days. For the first 5, that's 2 half-lives, 10 days. That's 3 half-lives, 8 days. That's 4 half-lives, 20 days. That's 5 half-lives. So 5 divided by 45 divided by 5. So then I'm going to go 1 half. And it's going to equal 5, right? So that's 1 half. So then R is going to be equal to S 1 and okay. I see these together. But in this case, it just depends on how many half-lives you put. So let's say, for instance, if we went to 1 half-life, how much? But no, 1 half. What's that? 8, right? After 16. If we went to 2 half-lives, it would be starting out with 16 half-lives. So we do it in 4 seconds. It's half. So first half-life is it would be 8. 16 to 8. Right? So that would be the first half. Second half-life from 8 to 4. That's right. Yes. Let's get that. Someone's a little bit practice. A little bit on the last week. I can still see where it's because you can always say it says 8 half versus 1 half. This is how many days it takes for 1 half. This tells us that it's over 25 days. Okay. Did you say half life? Half life. I think you're half life. Half life. Okay, so the next question. It says the half-life of potassium 45 is 18 minutes. If you have a sample containing 2.1 times 10 to the third micrograms of this isotope by Newton, how many micrograms will remain after the clock? You have to. Few minutes to work it out. Really don't. We did it. Right. I know. At least,
Yes.
but, oh, yours. So now, that's very good. Okay. Ready? Right. So, what I'm trying to do, so that's 1, 2, 3. That's 3 hours. So we have 3 hours. So yeah, 3 hours that we're working. Right? So we have to change hours to minutes. Hours to hours. So 180 minutes altogether. Right. So then you told me that I have 18 minutes per half. So I go in, and it's going to be 180 minutes divided by minutes. That's it. So then I use that equation. That's 1/2 n is r. Our starting was 2.5 times n. I can forget. That's the simple times 1/2. Okay. What did you guys say? Oh, So I'm gonna say fish cat. What did you guys get? What did you guys get? Well, that you haven't got it yet. Plug it in. Okay, so the way you plug it in, you go 2.1 3, and then go times. I go 0.5, and then there's a symbol that says XY. Okay. That's like but
Oh,
that's also but that's equals or XY. Yeah. Yeah, no. That's base. 0, 0. No. So, yes. You're off. So that's good. Yeah. How's it going over here? But hey, I was Right there. I don't think. I really did that. I know you're out. I'm looking at this.
Well, yeah, that's what I mean.
That's oh, that's good. Good question. Okay, so we were talking about the question was, how do I determine the number of significant figures, right? So when we're talking about time, talking about every clock, those are going to be considered exact, right? So that's not like saying you could have any number of say exact, or you can like 0, 0, 0, 0, 0, 0, 0, 0, because those are going to be exact, right? Now, 18 minutes, how many seconds are there? 2 seconds. So that means you always go with one that has the smallest number of bits. You have one that has infinity, you know, and then you have one that has 2, which is smaller. Infinity for 2. 2. So that means you have 2 sig bits, so you're able to divide 185. So then I should have this point. So that's the exact, right? Then we come here, we're going to 2 sig bits here. Right? So that means that we have 2 sig bits here, multiplied by a number that well,
I'm excited to see the different.
Sometimes, yeah, you always say it's multiplication or division, you always say it's smallest. Or what do you say? You ever bet money? Yeah, these are gamblers now, right? You lost a bet, yeah. I'll tell you what I want. What's that? I know. Sorry. Yeah. You're asking how we're excellent. So, yeah, okay. So, so that's yeah, I would. That's yeah, I could it's wrong. It's actually 5. Remember, it's exactly 5 and you love, right? You don't have that. But if it's something following, like if it's 5.001.
Yeah.
They remember.
No, I realize that. Well,
You think that value.
you say that at 5 space thing.
It's that.
In certain scientific
significant weight.
Oh, that.
Yeah. But I said it's exactly 5. It stays the same. But if it's anything following it, stop. Right? Because it's greater than 5. Right? Because we had that discussion before. Yeah.
And then you said that in school they were teaching this.
That's right. So if it's 5, 5.001. Isn't 5.001 greater than 5?
Just your
So they're absolutely 5%. That makes sense. Okay. How you guys doing? Pretty good so far? Okay. David, how are you doing? David. Okay. So we talked about carbon vision. So we talked about carbon vision. We talked about carbon vision. We talked about how it ages. I gave you guys the example of David. David being young and being old, right? So we can sit there and determine our age based upon the amount of the carbon ice. So I told you guys carbon 13 is actually carbon 14. Carbon 14 is greater than carbon 13. And so, but it also is very stable, lasts for a very long time. So if you look at the ratio of carbon 14 to carbon 12, because carbon 14 stays around for a very, very, very long time, it starts to accumulate, right? And carbon 12, I mean, it's the most abundant one around anyway. It's going to be around, which is that ratio increases. That means, okay? So you have more carbon 14 over 12. Okay. So our ratio in living organisms stays, it changes, right? But you still can tell, you still can determine, it changes, but as you start to die out, or the bones are around, all right? As we get older, as someone that teaches us bones get older, they start to accumulate some of that carbon, right? So living material basically has a steady flow, so it's constantly changing. So carbon 14, carbon 12 ratio is almost the same with my bones. My bones are a little bit older than David's. Some of my early David's. Okay, so the next thing that we're going to talk about is actual radioactive. So we have a radioactive material that happens that it decays, it breaks down. So as it breaks down, it will break down until it's to the point that it reaches a stable atom. So if you have an atom that's radioactive, it will break down until it reaches an atom that's stable. I'll show you an example of this. Okay, now this breakdown is conversion from one atom to another atom, to another atom, to another. That's called transmutation. Why do you think it's called transmutation? What is transition? Oh, yeah. Yes, or change, right? So in other words, we're changing, we're mutating, right? Okay, transmutation. Okay, so here's an example of radioactive material. At the very top is really hard to see anything. The very top is uranium-238. Uranium-238, it takes 10 years to decay, right? But when it decays, it goes to thorium-234. So now this process of decay is going to be an alpha decay, right? So, do you mind if I use the board? You get the board for me? It's no, it's share. Here, let me stop sharing. Or actually, Okay, now hit share. Then hit whiteboard camera. All right, virtual. There you go. Okay. Yeah, I want you guys to do this calculation. In 2 weeks, you'll be great. Imagine it. I mean, I'm sure. So we have uranium 238. What is the atomic number for uranium? Atomic number for uranium. What's that? 92. Okay, so it's 92. So I told you that it's going to be an alpha decay. So if there's an alpha decay, what's going to be lost? Alpha decay.
Positive.
It's going to be an overall positive charge, but what is it going to be? What's the symbol? Oh,
There we go.
there we go. Okay, so if I'm losing a mass of 4, so basically I'm subtracting 4 from this number. What is that mass going to be? 234. And then I'm subtracting 2 from this number. What is that? Okay, now I want you to look at the periodic table. Who has an atomic number of 90? 90. You guys just need to very first alpha decay. That's an example of an alpha decay. It's game. Shots. Shots all around.
Yeah.
Oh, I love contests.
Oh, so this would be an example of like alpha.
This would be an example of alpha decay. Okay.
No, I
So okay, so let's say we have the thorium. The thorium goes to a beta. So what was it? You said a minus. So what would it look like? It would add a 0 with all the minus. Okay. Like that. Okay. So in this case, I have 90. Right? So what number minus 1 will equal 90? 91. Okay, so I have 91 here. Okay? And then this is a 0, so we just take that across. 234. So 91 would be proactive. So PA. Okay, proactive. Okay, good job. So this is an example of a beta decay. In the case of a beta decay, what ends up is that you add an additional proton. It is not working.
I have a question.
Yes.
So part of it, like we have to ignore it.
It's always a little because that represents electron. Don't do that.
So, we're using electrons, right? Like, that's like perfect. And then you negative, positive, that's bad, right?
So in other words,
Are we gonna do it
in other words, this has to add up to this. Can you guys see? -1 plus -1 has to add up to 9.
Oh, because remember the thing on the next like, they're not equal to the
Yeah. So this is kind of like a law of conservation of energy, right? The only thing is that it doesn't quite equal to energy because that's the reason why nuclear energy is a little bit different. But if you look at it, it still adds up to the same. So what you put in is what you have to get out. Does that make sense? Okay. So this is a different way, but it's only in the context of the nucleus. This is all movement. That's right. That's right. Okay? And so we also know that this, the mass is half of that, right? Okay? Does that make sense? Is this a negative? Oh, no. No, because I would not add up. Yes. It's like, I don't know how that adds up.
for the video, for your
No, thank
content?
Exactly. Okay, questions? Concerns? Catch? Okay, you guys ready to move forward? Okay, so those are examples. Now, if I said I'm going to have gamma, let's say we have TH with a star in front of it. This basically means it has energy associated with it. Gamma decay would just be this. That's all gamma decay. It doesn't do anything, right? It just releases that gamma ray. Okay.
where we have gamma decay.
Go from a star to no star. No, I'm sorry. Yes,
I have a question. And what all it that were the opposite of doing or they gas that's
Yes. Okay, you guys ready to move forward? You guys got it? Feel comfortable? All right. Okay.
Yes. Oh.
Okay, so let's see if you guys got this. So.
Yeah.
Yeah, you're ready. Good. So I need your equation for the addition of a beta particle from this one to 10. Beta. So addition is release. That means, right? That means produces, right? That's right. So release. Right.
Oh, this feature? Oh, yeah, that's it. Oh.
Yes. Okay, who's gonna lead the discussion? Right. Oh. So it's a beta particle, so it's negative. I missed it. Remember, we had our nuclear reaction, also it's the heel stuff. but make it bigger so that it looks like a reaction. And keep some space, give yourself some space, so it's not right on the real side. If it looks like a real sign, it's a 0. I'm gonna make it right. So then what is going to be the other part? The other part is 0. Okay. And why is it? Because we're missing 0. So then you have to say plus, because there's 2 of them, right? So well, plus. Okay. Thanks. Okay, so now equals 0. Okay. Questions? Concerns? Yeah. Oh, good.
Wait, so, do you have to put that block, the sign there?
Yes, you have to put that plus sign on, because if you don't put the plus sign, you're not saying that, because you have a beta particle and you have a one here. I see. So both of those exist. You don't put that plus sign, that means something entirely different. It's kind of like a chemical reaction. If you put H2O plus, you put H2O plus NaCl, we know that we have some water. But if we put NaCl, H2O, that's something different. Right? So you always want to put that plus sign in the things that are there. It's this and this. That plus means this and this. Okay. It's kind of like if I put your name, her name together, right? You think that's one person rather than you and her. What's that? It's believable too. Okay. Questions? Okay. If you have questions, you ask them now. Okay, so chemical reactions. Chemical reactions and reactions are chemicals are that the chemical properties are going to be isotopes of an element in itself. So, in other words, if you have the isotope carbon 12, carbon 14, their chemical properties are going to be similar. Where we have the nuclear properties of isotopes of an element are going to be different. Well, carbon 12 is going to behave differently than carbon 14, right? In terms of the nuclear. Now, chemical properties are going to be dependent on electrons on the outside of it. Where we know that in a nuclear reaction, we're dependent on the nucleus. Okay? So it's going to be the radioactivity is independent of that chemical combination. It's going to be only dependent on the nucleus. Okay, in the case of a chemical reaction, atoms are going to keep their identity, but they're going to be able to change compound that they're in. So chemical reactions change. In the case of a nuclear reaction, the results is going to be the formation of different elements. So, like in the case of bismuth, it broke down to ammonia element. Right? You guys see that? In the case of a chemical reaction, the amount of energy is well. Now this is a relative. No relative. So a chemical reaction is very possible. But in terms of what you get from a nuclear reaction, it's going to be very low. So we're talking about a blue scale here, this way. Well, the top of the buildings. Where we just roll a whole wall. How you guys doing? Okay, so this is an example of a particular type of nuclear reactor. It's called nuclear bombardment. In the case of nuclear bombardment, is that you're basically putting an alpha particle with something else. So in other words, we're going to do what we call fission, fusion, pull things together to make an element. So this is an example of fusion. Okay, so if we take a look here, we have beryllium 9, and then we're going to add an alpha particle. Okay, so as a result of this, we're going to end up with carbon 12. And we're going to get what we call the radionuclide. This here is just basically a neutron. Okay? So look at the numbers. Again, at the top, it adds up to what? Oh, it adds up to 13. Then on this side, it adds up to 13. Then we look at the bottom. Bottom adds up to 6. And then on this side, it adds up to. Okay. Questions? Okay. So the major thing that you get out of this is that you get a stable. This guy's going to be a stable nucleus. It's going to be a stable isotope. Okay. And then also okay. Positrons are going to be subatomic particles with a charge of +1, and they're going to have the same mass as very, very particle accelerator. So particle accelerator is the device that needs to use electric fields so that it basically a lot of plus and minus charges electric. And so you're shooting the particle. It causes this particle to speed up, and then you use this particle to bombard another element. And so either you're causing it together, that's what makes it work. Or you can use it to split. So that's what a particle is. That's how it is. So nuclear bombardment is basically the production of another application, right? Or by split. So transuranium is elements that are beyond that are greater than. Uranium is one of the isotopes of the properties. That's not here. Uranium and consider. So that's straight back. Arsenal. Okay. Radioisotopes are expressed with battery for battery power and smoke detectors. They're used for preserving food. They're used for just getting into general. They're used for scientific research, archaeology, studying water plants. They're used for studying metabolism. So, archaeology, study of fossils, old stuff, old trees, old youth. Okay, smoke detectors. So in the case of a smoke detector, here we basically have our radioactive source. That radioactive source is going to start this messing with the ions, which causes energy to flow. So as smoke is detected, it will disrupt that. Okay, and as it disrupts that, remember how the vapor was being pushed in there and towards thing, right? Smoke does exactly the same. So it'll start moving towards it. As a result of that, because it starts disrupting. Okay. In the case of nuclear fission, so fusion is when we're putting things together, something. Fission is when we're splitting. So in this case, we're taking a neutron and we're going to be shooting this uranium, splitting it into two different isotopes. So in this case, we're getting strontium 4, xenon 139. And then we're going to get 3 additional neutrons. So these 3 additional neutrons can cause group chain reaction. We have that 1 neutron that first half. And if we have more uranium in our solutions, those 3 neutrons, because that one that was split is speed up because the other was shot out. So those 3 neutrons will shoot out, and then they would get another rate. Depending on how they get it, they have a different product. This is an example of a chain reaction. So if you guys take a look, hard to see, but here's that first neutron. That first neutron causes these to split. We're getting barium and right? So we get 3 more neutrons that are shooting off. Then we get that is another atom or isotope, and then we get 2 more. Okay, and this one is this guy, and then so on and so forth. In other words, we're getting that uranium is getting some of these 3 neutrons. So depending on how it is, it's going to split that out. So this way is the krypton, this way we have antimony, niobium, this way we have xenon, thorium. So it just depends on how it is. Yeah. You're not guaranteed. So it's kind of like Firebaugh has. Right? This has a lot of things. And you're not a good agent, right? So you may do it, and it may get the one of the case. You may do it, and it may get the one of the back. You may do it, and put it in the liver. Right? So it's exactly that case. You're basically throwing this neutron, and it, depending on where it is, it's going to cause it to split. Okay, makes sense? And so, and at the end of it, we get 2 or 3 neutrons that are shooting out, they're going to hit somewhere else. Okay, so nuclear power is basically using that splitting of the atom. And because you're splitting the atom, you're generating a shitload of energy. But you're also generating a lot more radioactive waste because you still have these isotopes that are radioactive. And you're splitting it randomly, so you're not always getting something stable. You're going to get a lot of stuff that's not stable. Right? But you get a lot of energy. So it's a trade-off. Okay. So we have what we call control rods. Control rods. They're going to absorb those neutrons. So we're able to get some of those neutrons that control. Moderators. So it's going to get stuff that slows down the speed of those neutrons, because otherwise if they're going too fast, they will produce way too much. That's more. And then you also have to think about it. This energy that's going to generate from this is going to be so hot. Right? So it has to be concealed in a certain way. So this basically is a schematic of the plant. You guys can see the control rods here. You have basically water. Speak that. It's water reactive. We're also using it for power. Okay. So you can imagine what are some of the issues that you associate with that? What's that?
What do you say?
I said, what are some issues that are associated what can be some of the results from that variation? What's that? Yeah. So the idea is that it should be still generating random stuff, right? So you have a lot of nuclear waste. Right along the right line. Right? So in other words, you have more nuclear waste than you actually started. You have uranium. Now you have all of these random components. You don't know how they get apart. So you're generating components. It's nuclear waste. That's one. So what else? So what happens if that radioactive waste gets in contact with flash? Explosion. Right? It's an explosion, especially if it doesn't go off properly. What else? There's nothing. What was that? Acute radiation signal, right? So if you get exposed, you're working at that plant, that happens to you. That's right. Yes. So you guys are Chernobyl, right? That's well. What was that? Yes, actually, we still have only one. So. Okay, so here's the pros and cons. Pros, it produces a large amount of nuclear power. It also doesn't produce any greenhouse gases. And there's no need for petroleum. You don't have to worry about gas. You don't need gas. Okay. Cons is that there's threats of accidental release of the radioactive material. The disposal, where are you going to put it? Okay. So as you make this, all these random radioactive isotopes, where are you going to put it? Or to decay. They store it. Store it in certain places. There's certain places that don't have a lot of you don't get science. So they're called reducts. And he's talking about trying to shoot to the sun. They're worried about moving defects, something that's radioactive, which they have other things in the science that cause a lot more reactions. Just do it. Yeah. What's up? Okay. And then the other problem is that you're always worried about houses here. Right? You're responsible. So these are all the countries that basically use nuclear power. Right? And you can see we're in the US. We're ranked 19% of our data. That's the food stuff that we're being. We're actually in military bases. These are all military bases. What was that? Oh yeah, they used to buy. Yeah, it's about 77%. That country good. Self-sustaining. Their guys were like they need gas because of cars and everything, but they're not as reliant on petrol. So in other words, if you guys go to France, they don't have a lot of chemicals. Gas is very expensive in Europe. Because most of it is houses, stuff, all that's going to be done.
So plants grow less. But
So if you expose immediately for a large amount of
then where it's not.
no, plants grow fine. Yeah. Because their plants are designed to withstand it. Yeah.
Or it just kind of overnight.
No, because you're looking at it as exposing atoms, exposing atoms. You take the tank. So the nuclear energy, the nuclear isotopes afterwards think so in lead. So a lot of these buildings are made with a lot of lead or deep high build, line with lead and other materials of lead. Yeah. So lead is great because lead is so project not able to cause that to so it doesn't radiate on its own. So it's good for tank. So these plants are lined with lead, so you can't really react with it. So then what they do is they have people bring these back to the waste, and they'll put it in the bigger, spit it off. And so,
No, I don't. Yeah. And all right. Or like not like I'll use gas and gas or stuff. But like it's a good part like you do like well just that waste. You know how we use gas too like for does it last longer for them?
all right, so there, nuclear energy is so funny. Because you can, from a single existing atom, justify get from a single molecule. Talking about so in that context, they're more energy efficient. They also don't have, they have an issue with global warming because of global exchange. Cool. Let's just doesn't affect environment as much as that for still that radiation. So you go on and make one of the reasons why we don't because our infrastructure. So what happens basically the forces they basically knock out a lot of that gas so they could reuse their fuels because they're going out so it's ready. They said, well, why are we they come in and start.
And also the issues right here why we need to correct the gas and keep it going.
Because okay, so the next type of reaction is called a nuclear well, we're going to talk about it. That's the composition. Yeah, usually nuclear fusion is you have two small nucleus. So in this case, we're using deuterium and tritium. Both are isotopes. They're come together as and then okay. So take a look at this. That's up to the top. This side has black. And then bottom here. The bottom here. Okay. And see the trend? See how it works? Okay. So now fission over fusion. Fission is what again? Fusion is what it means. Yeah. Fission is breaking. Okay. So the advantages of fusion over fission is that fusion will give more energy for atoms. Okay. We have an abundant supply of the fusion. So there's no radioactive waste. And then the disadvantage is that it's really, really high temperature. You're going to need high temperature. And then that basically means that if you're using such high temperatures, we have something that's able to run the atoms. So the problem is that, hey, it sounds great on paper, but right now we don't have a bell or a type of container that is able to sit there. Ready enough, be ready. We build one time, one done. But so much. Okay. Question. Yeah. Okay, good.